Recording, it's rolling. It's Tuesday, May 12th. Right, so yeah, last few days have been going over solutions. Now, there's a whole solutions packet. You guys in front of me, hand you a packet. Want to take it, you can have it. So I've gone over these more slowly on video a few times and posted those videos to Google Classroom. Also, there's a YouTuber, Alan Sal, a STEM coach, who posted solutions to his channel on YouTube, and I linked those. And he got the exact same answers I did, so right, that's a good sign. We're all getting the same answers. Okay, so anyway, if you guys want to see how you did, you have the solutions packet, you have videos, you have links. It's all in Google Classroom. Now, since we have just a few days of school left, I've been wanting to teach you guys about electricity and circuits. Here, I'll do a quick demo with you guys with some Christmas lights and a battery. Okay, guys, this boxy looking battery. How many volts is this? How many volts? 9. It is 9 volts.
Thank you.
Okay. Actually, what would happen if you lit a 9-volt battery?
It would shock you a little bit.
Yeah, it shocks your tongue a little bit. Okay, so I'm not going to do that, but I will hook up this Christmas light here. And oh, look how bright! Look how bright! Ooh. Hey, guys, what if I have a whole string of lights? Let's go. Okay, let's do one after another. One after another. Remember how bright one bulb was? What do you guys think three in a row is going to be?
Less bright?
Less bright. You're right. It is less bright. Yeah, look at that. They're lit up. They're fairly dim. Okay. Now, here's another way to wire up 3, where all the leads are connected like this. Right. Oh, there's technical terms for these. 3 in a row sequentially. This is called in series. 3 resistors in series. This is called 3 in parallel. How bright do you think these are going to be?
Bright. Very bright.
Ow! Ooh, each individual bulb is extremely bright, and so all 3 are super bright. Ooh. What about something like this? Look at this string. It's like a square. Ooh, do you guys see that? What if I hook up leads right here? What do you think is going to happen?
It's gonna blow up.
Blow up? Oh, well, I probably wouldn't be holding it with my bare hands, but otherwise, good tip. All right. Hey, look, this one closest to me is really bright. It's getting all 9 volts across it. But look at these 3 guys in series with each other over here. They're also lit up at very, very dim. Huh, that's interesting. Okay, so what's going on here? So let's go back to the beginning. I have a balloon. Right? Guys, if I rub this balloon against my hair, you guys ever done that? Rub a balloon against your hair?
Yeah.
Ooh, it feels all chargy. Okay. Let's see if I get an attraction here with this metal. Oh, that's really strong today. Some days works better than others. Working really good today. Okay, can I stick this to the wall? Sometimes I can. Yeah, it's working today. It's gonna stick to the wall. Ooh, good. We got an attractive balloon. What about? Okay, I got a couple of strips of tape here. Okay, is that still going? Yeah, we're still going. Clear all this off. Got a couple of strips of tape. What if I strip these apart real fast? Oh, I just meant to stay with the balloon. The balloon tends to attract electrons, and hair or animal fur tends to give up electrons. Okay. It's a different charge response. What if I strip apart these tapes? Okay. Now, what usually happens is that one of these grabs a few more electrons than the other. So if I pull them closer together, what are they going to do? Attract or repel?
Attract.
Should attract. Yeah, I see I see some attraction there because they got opposite charges. Now, which one's which though? I can find out with the balloon. Because I know the balloon wants to be negatively charged. Remember, this latex wants to pick up negative charge. Okay. Let's see what this tape is right here. Oh, there's a strong attraction. All right, I didn't know which it was going to be. Guys, if this balloon's negative charge, what does this tape have to be? It has to be positive. So if I put this tape down and I bring the other strip, this is the other tape, what should it do with the balloon? Should it repel? It does. Look at that. It's getting pushed away. You guys see it's getting pushed away from the balloon? Right? Now, what you're seeing then is that you're seeing evidence all over that like charges want to what? Yeah, repel, and then opposite charges want to attract. Okay, so we have that. Go through some slides with you guys. I have some slides. I have demos. Got some Hewitt eventually. Is this? Here we go. Okay. So let's look at variables and units. So if I talk about electric charge, like if I charge up a balloon or maybe an electron has a certain charge associated with it, we're going to quantify that in coulombs. Right, so the variable is Q, might be lowercase q, here's capital Q, right? And the unit is capital C. Right? Now electric current, guys, the letter C is used all over the place, so we're going to use capital I to designate electric current. I bet somebody knows. Guys, what is electric current measured in?
Watts.
I don't think I've said the word yet today. Starts with an A. Amps. Aha! Amperes. Amps. Right? But what is 1 amp? Turns out 1 amp is 1 coulomb per second. Right, you guys know the whole metric system, all the units relate to each other. Yeah, okay, so if you take 1 coulomb of charge and flow it on a wire, say, per second, yeah, 1 coulomb per second could be 1 amp. All right. Now, why would there even be an electric current? What would induce the electricity to flow at all? Okay. Well, it's because there's some potential difference or some voltage. It's going to be quantified in volts. What is 1 volt? Well, it turns out to be energy per charge is what it is. Right? Hey, that's like that 9 volt battery. Because you were looking at a 9 volt, that Boxy battery is 9 volts. Oh, I meant to mention too, is what about a double A? Does anybody know how many volts is a double A? It's like 1.5. Right? Same thing with a C cell or a D cell. Those are all 1.5 volts. Right? So different batteries depending on the battery chemistry. Okay. Now, ideally, in a circuit, you also want a resistor in the mix, and resistance is going to be measured in ohms. There's the Greek letter omega for ohms. Okay? And those were those Christmas lights. Those Christmas lights. Okay? And how much electricity ends up flowing? Here's one you know from last semester. You guys remember power is measured in watts? A watt is really a joules per second, so it's a rate of energy transfer, isn't it? Okay. So here, go back over here. Right, so, yeah, here's my double A, it's 1.5 volts. Here's my Boxy battery, which is 9 volts. Right, 8 times the voltage, what, 6 times? Okay. Guys, do you ever want to do this? Take a bare paperclip and touch it across the leads of the 9 volt battery? Okay. If you do that, you can't do that very often. Maybe I can touch it, but I don't want to do that too often. Because what it'll do is the paperclip heats up really hot, really fast. Like if I kept there for like 30 seconds, it'd probably burn my fingers. Yeah, and it's draining the battery really fast. Because this metal right here has almost no resistance from that lead to that lead. So I'm creating a circuit with almost no resistance. Right, so that's called does anybody know what it's called? Starts with an SH.
I don't know if you're wrong.
Because if you drop your phone and a vat of water, it's gonna short it out.
Yeah.
It's creating pass-through electricity where it's not supposed to flow. Yeah, so that'd be called a short circuit. A short circuit is where there's no significant resistance, or there's no resistance. Right. Like if I put a thermometer on it, I don't know, but I think you could start a fire with it. So if you're like out in the woods and you didn't have any way to start a fire, but you had a 9 volt and a paperclip and like some dry leaves, yeah, you could start a campfire that way. Yes. Yeah, you could. And then here's some other things you can do. I don't know quite get to those, and because we only got a few days of class left. Right? I've got magnetic field. You can quantify in Tesla how strong is magnetic field. Right? How strong is Earth's magnetic field is way to quantify that. Right? All right. So here, look at a couple of charges here. Now, if you say what's the electric field from a single charge, there's kq over d squared. K is an electrostatic constant. Q is what's the electric charge in coulombs. D is how far are you away from that charge, so like distance. Right? Notice it's an inverse square law. Do you guys notice with the like charge, like plus and plus, you guys notice these field lines never cross? See that? That's interesting. If I go back to the previous slide, plus and negative, those field lines want to interact, right? So it looks like we're drawing from plus to minus, maybe as a convention, right? Those positive charges, all the field lines, so it's like we're drawing the arrows going away from them, but they don't cross. So like that. What about a different perspective? Not electric field, but what's the resulting electric force? Now here I have to have 2 interacting charges. So that shows up in this format. I got a Q1, but also a Q2. Got 2 different charges. Right. And here's your electrostatic constant right here. Right. Hey guys, does this look sort of like universal gravitation? You guys remember universal gravitation went like G_mm over r squared? So it's really similar looking expression right here. Really similar. All right. So when you're seeing circuits, now electricity, it's invisible. You have to use your imagination. What's going on? We've got voltage, we got current and amps. Right. So when I learned this back in high school, it's really clicked for me when I learned this particular analogy. When you see voltage, think like pressure. So that battery is acting like a pump, right? 9 volts is trying to get the electricity to flow like 6 times more than a double A at 1.5 volts, right? So it's like 6 times the pressure. You can think of it that way, the voltage, the potential difference. Okay? Those Christmas lights you could think of as being resistors. Remember, you want some resistance in your circuit. Think of it like being a crimp in the pipe. And then the current that flows in amps, think of that being sort of analogous to a flow rate of water, like how many gallons per minute, like that. Now you have a nice analogy. Right? Another analogy I'll use for current and amps is imagine traffic flowing around a town. Right? So every car could represent like an amp of current, so something like that. Okay. The current that ends up flowing is directly proportional to the voltage, the potential difference, and inversely proportional to the resistance. This is called Ohm's law. Sometimes you also see this formula written as V equals I times R, or sometimes instead of V, you'll see an epsilon. So there's variations on this, right? But Ohm's law, how much current flows? Well, more voltage, more current, more resistance, less current. There you go. Okay? There's also Joule's law. Say, what's the power in watts? Guys, here's 3 different perspectives on Joule's law. You go current times voltage, current squared times resistance, voltage squared divided by resistance. If you substitute in Ohm's law for any one of those, you can get the other 2. Right? Any one of these might be the most convenient formula to use, depending on what the setup is and what the question is. Got this analogy. All right, so like a pump here. Okay, oh, guys, how about a flashlight? Let's create a flashlight schematic. So wherever you have a battery, you can represent that with 2 parallel lines, one longer than the other, and the long line represents the positive side, and the short's the negative. Okay, it's just symbols people came up with. This jaggedy symbol is a resistor. A classic example of a resistor could be my Christmas light, a light bulb. Okay? Here's another symbol, a switch. So if I hit on, like an on switch, I'm closing a circuit, and now the electricity has a path to flow around. If I close the off, if I hit off, that's going to actually open the circuit. So if you hit the off switch, it opens the circuit. Now the electricity can't flow, the bulb doesn't light. So there's a very basic schematic right there. Okay. Here's some demos in here. Let's look at, there you go. Okay. Let's see this electricity flowing around. So there's 2 main kinds of current. There's direct current and alternating current. It's DC and AC. So anything with a battery in it is going to be direct current. And guys, what's something in this room right now that has a battery in it? What? Laptop. What's another thing that has a battery in it?
Phone.
Your phone, which you don't have. What's another thing you have that has battery in it?
A clock.
Clock. Aha. What's another thing? How about those calculators on your desk?
Oh.
How about well, I have a wristwatch. I don't know. Does anybody have a wristwatch? Just me? No, maybe. I don't know. Right. Yeah. So anything with the battery, the electricity flows all the way around. Hey guys, do you think the electrons actually go from the negative side to the positive side? Do you guys think? Right. Here's a little technical historical detail. But back in the 1700s, Ben Franklin days, people didn't know that. They didn't know the structure of the atom. So they did a coin flip. They chose as a convention the flow of positive charge. It ends up being the electrons actually flow the other way. Oops, backwards. But where so mathematically it doesn't really make any difference. But it's just a convention that's carried down for hundreds of years. Right? But look at this one on the right. Look at this alternating current. You guys see that there's no net motion of either the charge or the electrons, if you want to think of it that way. You guys see there's no net movement on alternating current. Right? This AC is more useful for transferring electricity over an entire power grid. And the reason is that you can use a transformer to step up and step down voltages. So it's more efficient to pump up the voltage and have like thousands of volts on the power lines, but very low current. And then use a transformer when you're transmitting that electric current to, say, a building like the school, and step it way down with the transformer and make it low voltage but high current. So you can, there's reasons that works. Okay? But guys, you guys see this back forth motion? Back forth, back forth, back forth. Right? You have to have a convention for the entire power grid to make this work. Do I have? Yeah. Okay. Guys, what do you think that back and forth motion? What do you think the frequency is? Do you guys remember frequency in hertz?
Yeah.
Right? Guess. Let's see if we can see this slow motion with this one of these. Guys, see this pulsing? Pulse, 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 pulse. You guys see that pulsing right there? Do you think that means this light bulb is connected to an alternating current source? Yeah, probably is. Yeah, thank you. Yeah, you guys think it is? All right. Take a guess. What do you think the frequency is? In North America, it turns out to be about 120 hertz. About 120 hertz. That's what it is. Right? 120 hertz. All right. All right. Let's go back to here then. All right. So, yeah, I got a lot of my demos stuffed away, but you just have some breadboards open. You guys see some of these resistors. Whoops. Let me go back here. So, guys, if you see one of these in an electronic, some electronic components, say a little circuit board, you can read the bands, and the bands tell you how much resistance we're talking about. So we've got brown, green, red. Now if we go over here, I know brown represents the number 1, green represents the number 5. So the first 2 digits are 1, 5. You guys see that? 1, 5. Now the third band tells you an order of magnitude. The red band means the number 2, but in this context, it's the third band. It's really times 10 to that power. So 10 to the 2. Guys, what is 10 to the power of 2?
4.
100. 100. Right? So you read this as 1500. Guys, that's 1,500 ohms. Then there's a space and there's a fourth band, and the fourth band tells you the tolerance. So it's a plus or minus value. And in this case, gold is plus or minus 5%. So now I can read that resistor. Those Christmas lights I was working with, by the way, they're approximately 2 ohms each. Right, so we'll get that there. Right? Guys, there's different ways to wire up resistors. If you wire up one after another, that's called in series. And the total resistance, very simply, you add the resistor. So it's together. Right? All right, you guys good with that? So if I had 5 ohms, 5 ohms, 5 ohms, that could be 15 ohms. Here, let me show you guys again what that looks like. Right, so over here, guys, let's just do 1 volt. Right, so in case you missed this earlier. Right. Guys, look how bright 1 volt is on this 9 volts. You guys see how bright is 1 volt? Right. But what if I have 3 in series? Guys, there's 3 in series. And now they're lit up, but they're a lot dimmer, aren't they? You see that? Right. Now what we'll also do, it might be one of these slides coming up, is we're going to do parallel. Here, guys, take a guess. What do you guys think 3 in parallel is going to look like? Yeah, all super bright like that? I know some of you guys saw this earlier, but not everybody got to see this. Right? Yeah. Right. And there's different ways we're going to wire these up. We can create like hybrid circuits. Right. So let's get back to fundamentals here. What is this going to look like? The series in parallel. So are you guys okay with 3 bulbs in series, one after another? I can very simply add the resistances. Okay. Now, one of the analogies I'm going to use is a traffic analogy. This will be more helpful later too. You guys see this voltage source right here? This battery down here? Right. So let's use a traffic analogy. What if this was a parking garage full of cars? You guys see that? It's full of cars?
Yeah.
These cars are going to make a trip around town and they're going to come back to the parking garage. Okay. Guys, does every single car in this configuration have to go through every single of these stoplights?
Yes.
Yes, it does. Yes, it does. There's no escaping it. Okay. So if there's like 100 cars, all 100 cars have to go through all the stoplights. So that would be a good current analogy. Hold on to that idea for later. Right? Here's our parallel. Now, guys, let's go traffic analogy for a little bit, and then we'll come up with some formulas. Guys, imagine this parking garage right here is full of cars, and the car's going to make a trip around town, come back to the garage. But, hey, can the traffic split and the cars go through different stoplights? Do all the cars have to go through all the stoplights to get back to the garage? No. No, the traffic's going to split. You can go through here or here or here. So guys, if you open up more roads that are in parallel, because the traffic's splitting now, from the point of view of the cars, does that create more resistance? Does it make it more difficult to travel around town? Or does it make it easier to travel around town now that you have more passive that you can possibly follow? What do you guys think? Harder or easier?
Easier.
Yeah, I think easier. Isn't it easier to travel around town? Because if there's too much traffic on this road, you can say, well, I'm going to skip that and I'm going to go to this road and go through these stoplights. You guys do that too, right?
Yeah.
Right? So I think the total resistance is actually decreasing. Now, again, I got some formulas, but I want to do a little derivation with you guys. Here, I'm just going to steal my notes from last class. Okay. So, no, not. Well, you know what? Here, I'm just going to spoil this, but I'm going to come back to this. Right. Guys, so I'm going to make a claim here that 1 over the total resistance is 1 over each individual resistor added up, right? Or if you just have 2 resistors at a time, you can do product over sum. Yeah, I'll back this up in a minute, right? But what I'm trying to get to here is the next slide. Here, guys, go look at the slide, because the math is exactly the same. This is mathematically identical to resistors in parallel. What if I got a job to do, for example, painting a fence? Let's say you're Alan. Can everybody imagine? Okay, I'm Alan. It would take me 3 hours by myself to paint this entire fence. But I'm going to get some help from my friend Bob. Now, Bob, maybe he's a little slower. It would take him 4 hours by himself. But this is going to be a 2-man job, and we're going to be painting the fence at the same time. Okay. Guys, come up with a guess. Maybe an estimate. Approximately how many hours does it take these 2 guys together to paint the fence? What's a pretty good estimate? Who has a guess?
10.
You said what?
11. 140 minutes.
Well, good. One guy by himself can do it in 3 hours.
Or 40.
Okay. Yeah, he's getting help from his friend. Shouldn't it be?
There has to be less.
Yeah, it's got to be less, right? Right? Like, guys, what if it was 2 Allens? What if it's Alan and a clone of Alan? Should it be 1.5 hours? Right? What if it's Bob and a clone of Bob? How long would it be?
2.
Yeah, it would be 2 hours, right? So now if we have 1 Alan, 1 Bob, do you think it's somewhere between 1.5 and 2 hours?
Yeah.
Right? Yeah. So I'm going to make the claim here that it's 1.71 hours. Right? And let me back that up with some math. Okay, so I think we're ready for some math now.
That's like almost hour 40, right?
Pretty close, yeah. Pretty close, yeah. pretty close. Okay. So it's gonna go like this. For you to complete a job, it'd be the rate you're doing the job times the amount of time it takes to do the job. Is that okay? Like distance equals speed times time. It's really analogous to that, isn't it? Okay. So now to complete one job, let me say how much one job per the time it takes you to do the job times the amount of time that you're working to do that. Okay. Now here's the other calculus. Okay. Now let's say one job. Now we're gonna have two individual people. We'll have the rate Alan's doing the job times the amount of time painting plus the rate that Bob is doing the job times the amount of time painting. But now, since they're working on the job together, this time at the same time. So I circle that t, and I'm going to solve for that t. Okay. Okay. So next step, just do some algebra here. I'm going to factor out this t. Right. So I can do that. Right. And then I'm going to divide this t down here. And look what I have now. Guys, what can I cancel out? The unit job. So it's 1 over the total time is 1 over Alan time plus 1 over Bob's time. Get that? Right? Which is what I showed on the PowerPoint. This is just to back this up. Right? Now, if you just have two people working on it, say just Alan and Bob, right? I can get a common denominator, and it ends up being okay. So 1 over the total time ends up being sum over product. So when the time be the reciprocal, which is product over sum, is that true? Right. So whenever you have two people working in parallel, or back to electricity. When you have two resistors in parallel, you can very simply do product over sum. Okay, but that only works for 2 at a time. Okay. Now, if you want to bring in a third friend like Chad, and now Chad's going to help paint the fence, you can either do the reciprocal method, or if you want to do product over sum, again, you can only do 2 at a time. So you got to do Alan and Bob, write that number down, and then bring in Chad for another product over sum. Right. But yeah, if you got like a whole bunch of friends, like what if we bring in Derek, Eric, and Ferric? You can do plus 1 over time plus 1 over plus 1 over, and then you can get the total time for like a whole team of people. Okay. Okay. All right, you guys good with that? All right. All right. Here's a little bit more detailed. I got a very simple series setup and a very simple parallel setup. Are you guys okay with that? Now, there's these two rules that are called Kirchhoff's rules. Technically, there's just the loop rule and the junction rule. You guys see it says loop rule and junction rule, right? But there's a bunch of other consequential rules that fall out of this, right? That tell you exactly how does the electricity work its way around a circuit. So let's take a look here. The loop rule says very simply, if you identify any loop, the sum of voltages, sum of potential differences have to go to 0. For example, I have a 9-volt battery here. Everybody see 9 volt? Everybody see 9 volt? So it's going to pump up 9 volts. And then across this resistor, maybe it drops 6 volts. And across this resistor, it drops the other 3 volts. So it's down 6, down 3, and it pumps up 9. You guys see that? Okay. That's a very simple loop. This right here is a loop. This is a loop. This is a loop. Okay, so the loop goes to 0 volts. Okay. Now for a simple series set, here let's look at current through a series. We'll just stay on series for a moment here. Okay. The current is necessarily the same everywhere, even if these are different resistances. So guys, what if this is like 3 stoplights and this is 6 stoplights or something like that? Got 3 stoplights and 6 stoplights. Is it still true that the stream of cars, 100 cars, all 100 cars have to go through all the stoplights regardless? Yeah, and that's what this says right here. The current's the same everywhere in a series setup. Right? Now the voltage drops proportional to the resistor. So whatever numbers I was saying. Guys, let's say resistor A is like 6 stoplights. You guys see that?
35.
6 stoplights. Resistor B is like 3 stoplights. Okay. So would resistor A have 2/3 of the total resistance? And resistor B is the other 1/3. Okay. And that means the voltage drops proportional to that. So if I have 9 volts, I think 6 volts would drop across here, and the other 3 volts drop across here. That's all that says proportionality. Okay, you guys give it that. The voltage drop is proportional to the resistor. Right. Now let's look over at this parallel setup. Now for a parallel setup, necessarily the voltage drops are always the same across the resistors. Again, even if they're wildly different resistances. If you have like 1 ohm here and 20 ohms here, they still get the same volts across. So if I have a 9-volt battery, it's still 9 volts and 9 volts. That's actually consistent with this loop rule that I started off at the top here. Right. And that brings us to actually the other main rule. Again, there's only 2 rules. There's the loop rule and the junction rule. You open a textbook. Right. The junction rule says all the current has to add up and equate. So for example, guys, let's have 9 amps leave. Okay. Right. You guys see 9 amps leave the battery?
Yeah.
9 amps. Right. And the current's going to split. Okay, suppose 3 amps goes up here. How many amps went this way?
3.
How about 6? Right? Guys, 9 amps left. 3 amps went this way, so doesn't 6 amps go this way? If 9 cars leave the parking garage and 3 cars go on this road, do the other 6 cars go down this road? That's the same thing, right? That's the junction rule. That's all the junction rule says. Right? Finally, there's one more rule, and this one you have to think a bit more deeply on. But how does the current split proportional to the resistors? Right? So, all right, here, I'll throw some numbers again. Guys, ready for some numbers? Let's say resistor A here is 2 ohms. You guys see that? 2 ohms. And resistor B is 1 ohm. Right? Could that be like 2 stoplights versus 1 stoplight? Right? Now, guys, where do you think most of the traffic, most of the electric current is going to go? Is it going to go through 2 ohms or through 1 ohm? Guys, is the electricity going to follow the path of greatest resistance or the path of least resistance? Let's go with least resistance, right? Okay. How many guys think here? Show of hands, guys, look here. Show of hands. How many guys think that 2/3 of the traffic is going to go through the smaller resistor, and 1/3 of the traffic goes through the greater resistor? Right? Is it? Right. That's exactly here. I just gave it to you. Right here. Right. So the current that goes through branch A is directly proportional to the other resistor. So again, if I have like I think I said 2 ohms here and 1 ohm here or something like that, right? Okay, so it's actually, you guys see the subscripts are backwards, right? So it makes sense. You just have to think about it a little bit more deeply. Okay? Right. Right. Guys, let's look at some of these. Guys, look here. I want you to learn a little bit about circuits. Right. So let's do a straight series setup. So with a waterfall analogy. Remember I told you guys think of a battery being kind of like a pump, right? And these voltage drops could be like an elevation change. You're looking at the loop rule here because if this battery is like 9 meters high, could this be like drops 3 meters and 3 meters and 3 meters and see how the elevations match, right? Something like this. Right? But now we have water flowing. Now look, they're one after another, sequential. They're all in series. You guys say they're all in series? Okay. Let's do some numbers. Guys, look up here. I do have some papers printed out. I was going to give it to you guys possibly later this week, but we're going to find out. You guys might get a paper that looks a lot like this. Let's have a 12-volt battery. So you guys see my 12-volt battery? Okay. And I put on 3 resistors, 1 ohm, 2 ohm, 3 ohms. First number, let's get the total resistance for the entire circuit. Now, since they're all in series, can you very simply add them? Guys, I'm trying to help you out. Look up here. Okay. Can you very simply add the resistances? Who can tell me what's the total resistance for the circuit? 6, because 1 plus 2 plus 3 is 6. You guys good? Right. Now let's do a little bit of Ohm's law. Do I want to do that? Can you guys do Ohm's law? I said the current that flows is voltage over resistance. Guys, what is 12 volts over 6 ohms? 2 amps. 2 amps, is that right? Okay. Now there's different ways to go about filling out this table. All right. Guys, if 2 amps leave the battery and these resistors are all in series, it's a straight series setup. How many amps go through this here and here and here? 2, 2, and 2. Wouldn't that make sense? Yeah. Because they're all in series, that has to be the case, right? Now you can go through with Ohm's law and Joule's law and figure out the rest of this, right? Remember how I was showing you guys Kirchhoff's rules and the consequential rules that follow? Remember the voltage drop is proportional to each resistor? Hey, look at that! The greatest voltage drop pairs with the greatest resistor. You guys see that too? Right? As long as they're all in series. Fine, let's do Joule's law to get the power in watts. Now, one version of Joule's law was current times voltage. So guys, what is 2 times 2? 4. What is 2 times 4?
8.
8. What is 2 times 6? 12. Right, now those are all watts, power in watts. That might tell you something about how bright the bulbs light up if these were light bulbs. Right. Now, last detail. You guys see this very last cell? Let's do 2 perspectives on this very last cell, and they got to agree with each other. Okay. So one is we could just apply Joule's law at the point of the battery. Guys, what is 2 times 12? 24? So the battery should be supplying 24 watts, right? 24 watts, right? And the other perspective is, does supply match demand? I'm talking about electricity supply and demand, right? So how many total watts are being demanded by these 3 resistors? 24. Do you guys see if you add up all the watts, it's 24?
Yes.
Which has to be supplied by the battery? Boom, it is. So we just did 2 perspectives, and they both agree it has to be 24 watts. You guys see that? Right? Let's look at a different setup. Oh, hey, look, they're in parallel. Guys, when they just did this over here, did they all light up really bright in parallel? They did. Right? Guys, if it's a 9-volt battery, do all 9 volts go across every single resistor? Yes. Yeah. You can think of it like a 9-meter tall cliff. Up 9 meters, down like 9 meters. That sounds like the loop rule. Okay? So, guys, let's throw some numbers in here. Here, I'll do a little fast on this. Guys, look up here. If it takes one guy 2 hours to paint a fence, another guy 3 hours to paint a fence, and a third guy 6 hours to paint a fence, we got Alan, Bob, and Chad going on. They make a 3-man team. Make an estimate. How long would it take this 3-man team to paint a fence? What do you think?
45 minutes.
Oh, that's a pretty good guess, right? It has to be less than 2 hours, doesn't it? Alan could do the whole job by himself in 2 hours, but he's getting some help from his slow friends. So it's got to be faster than 2 hours, right? It turns out if you do the math with all the reciprocals or however you do it, it comes out to 1, or in this case, it would be 1 ohm. Okay, so from the point of view of the battery, it's as if there's a single ohm of resistance on the whole circuit. Okay, is that? Okay. Now, since you guys know it's a 12-volt battery, guys, 12 volts up here. What's the voltage drop across right here? Guys, what's the voltage drop? 12, 12, 12. Remember that was another rule? All right, guys, it's up 12 volts, down 12 volts. Up 12 volts, down 12. Up 12, down 12. That's the loop rule in 3 places. Okay? Okay, 12 volts. All right. Now you can go with Ohm's law there and Joule's law there, and you can finish this off, right? What if I have a hybrid setup? I can do something a little fancier. Okay. So yeah, possibly if there's a good opportunity later this week, I might give you guys a page where you have to do calculations like this, right? But you here I want to do a couple other things too. So let's do 2 things. I want to show you guys how a multimeter works, and then I want to play some talk demos for you guys. Okay. I really am giving you guys a short version of this strongly, but anyway. Okay, so guys, look here. So I think tomorrow possibly I want to get these multimeters in your hands, and so a bunch of these 9-volt batteries and a bunch of these Christmas lights. Okay. So let's take a look with here. Let's try this here. Okay. So if I want to measure voltage, guys, look here. I want you guys to learn something. Okay. So guys, multimeter means it can measure many different things. We're going to focus on voltage and current. So there's a black lead that's plugged in one called COM. I'm just going to leave this here. So black and COM, just leave that. Now this red one, right now I'm going to plug it inside, says volts. I'm going to toggle the switch over to volts DC. Okay, and let's see what it is across this battery. It should be 9 volts. Oops, give me 8.8. Do you get the 8.8 volts? Yeah, because it's a 9-volt battery. Okay, let's throw on some resistors here. Okay. Now I know my thumbs are kind of in the way, so this might not be the best visual, but yeah, guys, do the best you can here to see what you can see. What if I hook this up to right here, and let's say this one right here, if I can even get this to work. Okay. Let's see if I can get approximately 3 volts out of this. Sorry, is that showing up right there?
This is so millennium.
Okay. Sorry, it's a little
You want to hit the part?
getting a tentative connection here. Well, okay, 1.5 volts. It's about half of what it should be. You guys see that? Right. We'll just go with that. Okay. All right, now, guys, that was voltage. I was measuring potential difference. Guys, should it be? Right. You guys know it was 9 volts across the whole thing. Should it drop 3 volts, 3 volts, and 3 volts? Ideally, like, right? Guys, look here. I want you to see something else. Guys, I'm trying to help you. Look here.
I'm sorry.
Yeah, I'm sure you're very sorry. Now, the other thing I want to get out of this is what's the current in amps. So what I'm going to do is switch this toggle over here and switch this to milliamps. See what's the current? All right, hook this up right here. Now, guys, notice to get current, I have a completely different configuration. Notice I broke the circuit open. Look, the volts are off. You guys see that? Volts are off. Okay. I'm going to hook this black lead right here. And if I get the colors right, the positive, negative, then I'll get a positive value. Let's see. This should turn back on. Oh, look, the volts just turned back on. But you guys see how the multimeter is now part of the circuit?
Yeah.
You guys see that? Right, and it's reading 1.6 amps. You guys see 1.6 amps? So there's 1.6 amps flowing through the circuit. What if okay, look, they turned off. What if I cut these 2 out of the circuit and I connect this right here? Look, it's super bright. And also the current went way up, didn't it? You guys see the current's like way bigger now? It's like 2.6 amps. Is that? All right. So yeah, I'll see if later this week, possibly tomorrow, if we can get these in your hands.
No.
Okay, but let's finish off class with some Paul Hewitts here. All right.
Graph generator. It's named after a person by the name of Robert.
Van de Graaff. So he's going to charge this up. Did you guys see this a few weeks ago? I think I brought one out, right?
I saw
Some of these. All right. Now, okay, so he's going to create the sparks.
Notice I am notice that
You guys see the sparks? Right. Now he's going to take some pie plates. Right. Guys, a bunch of individual pie plates. They're all about to be charged the same. What's going to happen? Guys, what's going to happen? All the pie plates are about to be charged the same. You saw it earlier today with the balloon and the tape, right? Something like that.
And so the flow of current is proportional to voltage difference. Not how much voltage, but how much voltage in one place compared to the other. Think of voltage as a pressure, huh? So it's proportional to voltage difference. Proportional to. So the more voltage difference, the more. Hey, imagine I have a pipe right here filled with water. Okay, see that water-filled pipe? I have a piston over here, and I have a piston here. And I push with a certain pressure, maybe 5 units. I push with the same pressure here, 5 units. Which way does the water flow? How many the water ain't gonna flow at all? I say, yeah, I got under pressure. And you say, yeah, but there's no pressure difference. How about I push here with 5? And I push over here with 3. What does the water do, gang? What does the water do? The water flows, okay? And similarly, if you take a piece of wire and you put a pressure difference across the wire, and I can do that here. Here's a lamp, okay? This is a 12-volt battery. One end is 12 volts higher than the other. If I touch here and touch here, no light. If I touch here and touch here, no light. There's 12 volts, 12 volts. Why no light? Check your neighbor, why no light? Let's try the other side. No light, there's still no light. Why, how come? But I got 0 volts over here. Over here I got 12 volts. There's no difference. You gotta have a difference. Look at him, I go like this. A, ought to be, huh? What's the voltage difference across the lamp now? 12. So if you, hey, why is it that you see birds on high tension wires, bare wires, and you see the bird come down and he grab on the foot and stand on one foot and he's on the wire, and the bird doesn't get fried. The bird's okay. Now what happened? The bird reached down and put the other foot on the same wire. What happened to the bird then? Begin with N and with nothing. Try it. Nothing. He's a bird's okay. Look, hey man, the bird's 100,000 volts. Is the bird all right? The bird is all right because you get 100. What's the voltage difference across the bird? Zilch. This relationship, current proportional to voltage difference, becomes an exact equation when I include the idea of resistance. If you have a humongous resistance, even for a big voltage difference, the current will be very small. So how much current flows through things has to do with 2 ideas, gang. What's the voltage difference across the ends of the conductor? And what's the resistance that conductor offers to a current flow to begin with? And that usually has to do with the geometry and the material of the conductor. Like a great big fat piece of copper has less resistance than a little skinny piece of copper. Just like a great big humongous pipe will have less resistance to the flow of water than a little skinny pipe, yeah? And how about a lamp like this? This copper right here, it's relatively thick, but it's very, very thin in there where the filament is. Guess where most of the resistance is across these 2 leads? Begins with FIL. Filament. In that filament is most of the resistance. And guess where most of the energy is dissipated going from here to here when I touch it across the battery? Right in the filament. In fact, the filament reacts so bad, it turns white hot with heat. Look at that. It's glowing. And there's your lamp. Isn't that nice? So we measure current in amperes, amps, okay? And we measure voltage in volts. And we measure resistance in all together now. Oh. Okay, there's an ohm, yeah, that's ohms. In fact, ohms are written like this. Greek letter omega, ohm. Voltage is written like this, V, and current is in amps. The unit is amps, and oftentimes we call current I. So we could say I equals V over R. And it's the old song and dance, gang, that if you know 2 of these things, you know the other. Like, for example, let's suppose I tell you the resistance of this little lamp is 1 ohm. and I put it across this 12-volt battery. There are people in this room besides Lee who can tell me how much current is flowing through the battery. And then there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance, 12 volts across the battery. What's the answer again? 12. And that's 12 amps. That's Ohm's law. I'm going to hook this up like that. And lo and behold, it lights. What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room. And I could take these 2 leads and I could bring them to the other side of campus. And over on the other side of campus, I could go like this. And I'd say, what's the voltage across the leads, gang? What would you guys say? 12. And it would light up over there. In fact, what do you think a wire is? A wire is just 2 leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it and you're on. See, it's like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? I suppose I go like this, gang. I suppose I put another lamp in here. I'll put another lamp in series. Series, I'm using your word, gang, series. Huh? There's one right after the other. I should have asked you before I did it. Will a lamp glow brighter or less bright? And you guys would have said anyway, less bright. And I said, what's the voltage across the 2 lamps? And you guys would have said, what's the voltage across 1 lamp? And you guys would say, hey, feels good, feels good. 6. 6 and 6 is what? 12, that's right too. If you take the 6 volts across this 1 ohm, what's the current in there? Oh, we got to go through that again. If I get 6 volts across there and the resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series, how many amps right through this little point right here? How many amperes through a point right here? 6. And how many amperes flew through the battery? 6. 6. 6. 6. 6. 6. All the way along. How many amperes up here? None. This is not part of the circuit. My circuit's right through there. See what I'm saying? The current flowing through the circuit. And the circuit now has twice as much resistance as before. If it got twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do. And everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we got? It sure is dimmer. Let me ask you guys a question. What's the voltage across the whole system? 12. Okay. How much resistance we got now compared to before? 3. 3 times the resistance. How much is the current now compared to with the 1? 1/3. Ain't that neat? So now you got 1/3 of an amp. Huh? What's the voltage across one of these things? 1/3 of 12. 4. Okay. And 4. 1 ohm. Oh, okay. Do I have it right? Did I make a mistake? Did I make a mistake, gang? I never make mistakes. But we have 4 volts across here. Okay. 1 ohm. So we have 4 amps. What's going through here? 4. 4. Before it was 6, and first of all, it was 12. So the current's getting less and less because the resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series, but in parallel, like the rungs of a ladder, parallel. I'm going to hook this. What's going to happen to the brightness of that lamp when I connect this? How many say nothing? My people, that's right. Because let me ask you a question. What's the voltage across this lamp? What's the voltage across this lamp? What's the resistance of this? So what's the current through this? 12. 12. What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12. 12 amps, 12 amps, 12 amps. So amps, volts, I get mixed up again. The voltage is the pressure supplied by the battery, 12. There's 12 right through across from these 2 prongs, yeah? And I pick up the 12, 12, 12. The battery gonna wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here? 12. It's like automobiles driving from a garage down here. And some of the automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay? How many through here? 12. How many through here? How many through here? Ah, what is it? There's 24. Guess you get the 12 from here, and you get the 12 coming down this street. How many through here? 24. How many through here? You guys are on 12. How many through here? 36. How many through the battery? Who's getting tired? The battery. The battery. More energy going out now, more power going out. You get it? Okay? Think about these ideas.
All right, and then I was showing you guys the voltmeter and the ammeter, the multimeter here. How do you connect these? So maybe later this week when I get this in your hands, at the voltmeter, you're looking for a potential difference. You have to connect that in parallel. So you're looking for some voltage change. The ammeter, that's the one where I broke open the circuit and I forced the current to flow through the multimeter. So you connect that in series. Okay? Because all this electricity stuff, if you're going to be an electrician one day or something like that, obviously you need to know all the circuit stuff, right? But even if you're going to design, say, a water pipe system to go around a city, or a traffic system, or build a new road and see how does that affect traffic, you can take these principles too and help you design those things too. All right, so we're at the end of the class. See you guys tomorrow, and hope you guys have a good day. And if you have any exams going on, hope you guys do well on those.